Hello, today we'll be doing an AP Physics free response. We're doing number 2 from Form B from 2011. The question reads, the diagram above illustrates a velocity selector labeled region 1. It consists of two parallel conducting plates with charges on the plates as indicated, creating an electric field of magnitude E directed towards the top of the page. A uniform magnetic field of magnitude B1 directed out of the page exists between the plates. So here is B1, and this is the electric field E throughout region 1. The magnitude of the magnetic field can be adjusted so that only particles of a particular speed pass through the selector in a straight line. A radioactive source to the left of the selector emits charged particles. So here there is a radioactive selector, a radioactive source. The charge positive Q moves to the right in the plane of the page. The effect of gravity can be neglected throughout the problem. Part A. Derive the expression V equals E over B1 for the speed V of the particle that moves in a straight line through region 1. V equals E over B1. This is the equation they would like us to derive. So we can just use two equations that we know. Force equals QE and QV sine theta. In this case, theta is 90 degrees since the velocity vector is perpendicular to the magnetic field. So this goes to 1 and we can cancel that out since the sine of 90 degrees is 1. QE equals QVB. The Q's cancel. E equals VB. So we get that V equals E over B, and in this case B is B1. And so we got what they wanted us to derive. Part 2 of A asks us, some particles are emitted from the source with speeds greater than E over B1. Which of the following describes the initial path of one of these particles immediately after entering region 1? So if the velocity is increased, we realize that this will not impact the electric field, the electric force, because that's simply equal to QE. But it will impact the magnetic force, which is equal to QVB sine theta. And when we increase V, the magnetic force will be increased. So magnetic force will be greater than the electric force if the velocity is greater. And using the right-hand rule, we see that if the velocity is going to the right and the velocity is going to the right and the field is out of the board, so it's like this. The middle finger is the direction of the magnetic force. In this case, the magnetic force is down. So the magnetic force is going down and the electric force is going up. But since the magnetic force is larger, the charge will be attracted to the bottom plate. And so we can expect the charge to go down in and curve towards the bottom plate. And that was simply through the right-hand rule. Bottom plate, sorry. Alright, so that's it for part A. Part B says, a constant magnetic field of magnitude B2 in region 2, so here, is directed into the page and is now added to the right of region 1 as represented in that figure. Suppose a particle leaves the radioactive source, travels through region 1 in a straight line, and enters region 2. For each of the following, express algebraic terms, answers in terms of E, B1, B2, Q, and fundamental constants as appropriate. Part B. Determine the expression for the initial magnetic force on the particle in region 2 and state its direction. So the force is going to be equal to QVB2. And we can substitute in the V that we found in part A and we get Q is equal to E divided by B1 times B2. And as far as the direction of the force, this is the magnetic force, it's going to be the opposite of what it was in region 1, as you can see, because in this instance, the magnetic field is going into the board instead of coming out. So once again, if we do the right-hand rule, this is the direction of the velocity. Part C. Part C says, describe the changes, if any, in the magnitude and direction of the magnetic force as the particle moves in region 2. So what would be the difference between that point and that point, both in region 2? We realize that the magnitude remains the same because B2 is constant, the magnetic field, and the angle between the velocity vector and the magnetic field is going to remain 90 degrees, so the force is essentially going to stay constant. The only thing that does change is the direction. So for part C, we write the direction changes, but the magnitude remains the same. Part D, describe the path of the particle in region 2. Because the particle is going to be directed upwards due to the force going up, the magnetic force, and the magnetic field is going into the board, it's going to spiral up the page. For part E, they say derive an expression for the charge to mass ratio, Q of M, of the particle. So, what the force that this charge is facing is a centripetal force because it is circular. So mv squared over r, which is the centripetal force, is going to be equal to the magnetic force. So centripetal force equals magnetic force in this instance. The magnetic force we found here was QVB2. We'll stick to this so we can cancel out the V's. And then this becomes mv over r equals QB2. We are looking for a Q over M, so we can divide by M, B2 multiplied by R divided by V, and all we have to do is substitute in V, and we get E divided by B1. Hold on, sorry. That was incorrect algebra. 1 second. If we divide that by Q divided by M, we'll get V divided by R divided by B2, yes, sorry. And we substitute in V, which is equal to E over B1. And we get E over R B1 times B2, and that is the final answer for part E. Thank you.